Morning Year 12. I hope you got on okay with yesterday's lesson. Number theory, solving simultaneously linear congruences. Generally they're questions towards the start of the paper worth 4 marks or so. Today we need to look at a couple of technicalities and then also go on to solve sets of 3 linear congruences. It is of course able to use the same methods to solve 5, 4 more, but we only need to look at three sets of congruences. So to start with, 2 linear congruences to solve, so 2 individual congruences. So question 1, solve that. Question 2, solve that. So just to repeat, it's not particularly the way I've labelled it there. It is question number 1, question number 2. Okay, pause the video and have a go at those, please. Okay, so the first question should have been fine. List alternative 2 above a multiple of 14. We've got 2, 16, 30. Oh, 30, there we go. That's a multiple of 5. We must, of course, write down the HCF of 5 and 14 being equal to 1, so we're able to do that division. So you should have got x was congruent to 6 mod 14 for question 1. Question 2. Okay, I start by listing my 2 above multiples of 15. So I've got 2, 17, 32, 40. Oh, hang on. We, of course, are never going to get 2 above a multiple of 15 that's a multiple of 5. Of course we're not, because 15 itself is a multiple of 5. So we have this condition of no solutions. So what I wanted to do in this second question here was to remind you of what that condition was. So it's something you did earlier in the year with Mrs. James. A linear congruence of this form, so we can have, an AX here. If AX is congruent to B mod n, that's got a solution if and only if D, where D is the highest common factor of these 2 things here, the A and the N. If D divides B, then we have got a solution. So, but this particular question here, A is 5, N is 15, the highest common factor is 5. What we, of course, know is that 5 doesn't divide 2, hence the congruence got no solutions. So this is kind of what we would call the formal condition. However, in an exam question, if you were to state this statement here, 2 above a multiple of 15 can never be a multiple of 5, that is good enough to get all the marks of this question. So you can either do that or you can do that. Okay, so what I've got here, it starts off with that same statement, just kind of written a little bit tidier. So no, I'll put a star there because I'm going to refer to it later on. So that's the condition for a linear congruence. So let's go on to see what conditions we need for solving simultaneous linear congruences. So here we've got 2. Let's just have a little bash using our method and see what happens. So I write that second one, the one with the bigger modulus of 6 plus 12a. I'm going to substitute that into the first one, so I'll write it in the left-hand side. Reduce what I can, that's going to be a 3. I can subtract 2 and 6, so 3a is congruent to negative 4 mod 9, or I can just add on 9 there to make that positive. Of course, what I've got here is 5 above a multiple of 9. That can never be a multiple of 3 because all multiples of 9 are multiples of 3. So that statement I've said there, hence it's got no solutions. But what we can actually do is we can use this condition star here, on this line. That condition there is to say, so the D for this question here, or this statement here, would be the highest common factor of 3 and 9. Highest common factor of 3 and 9 is 3. And 3 doesn't divide 5, so there are no solutions. But of course, I don't have to use that line. I know we like that line because it's got a positive, the smallest positive integer, but actually we could have used that line. That line there. HCF, of course, is still 3, and 3 doesn't divide 4 or negative 4, so there are no solutions. So what we can do is try and adapt this condition in the green box to a set of simultaneous congruences. We use M and N, being the 9 and the 4 of the original. Of course, the highest common factor here is, just going to be the same as the highest common factor of those. So highest common factor is what we're going to call D here. And that negative 4 we of course got by looking at the difference. The difference of A and B, and it doesn't matter the way in which you do it, you can kind of do 6 minus 2 or 2 minus 6, we're looking at 4, we're looking at negative 4. If something divides negative 4, it's then going to divide positive 4, so it doesn't matter which way around you have it. So what we can do is either then go about solving it in the usual way, as we were doing here, but then using that condition, the condition that you looked at earlier in year 12. Or you can just go straight ahead and use this 2-star condition here. So either of those, again, they would be equivalent number of marks in the exam. Of course, that means that we have a particular case. If D equals 1, then that is always going to divide into that difference. So if the HCF of the two congruences, if you've got two linear congruences, then you're always going to have a solution. We're always going to have a solution, an integer solution. Okay, so let's look at a specific example then. So this one here, I've got x is congruent to 1 mod 12, x is congruent to 7 mod 16. So method 1. Maybe I haven't left enough space for method 1, but x is congruent to 1 mod 12, x is congruent to 7 mod 16. I'm going to call that number 1. I'm going to call that number 2. I'm going to start by rewriting statement number 2 as x equals 7 plus 16a. I'm going to sub into statement 1. 7 plus 16a is congruent to 1 mod 12. Let us reduce that, so that is going to be 4a. Subtract that will make it negative 6. And let's just make that positive. 4a is congruent to 6 mod 12. Now it's of form, so I can use that condition, that starred condition. So I'm looking at that statement there, that one at the top. I know that the HCF of 4 and 12 is equal to 4. And 4 does not divide 6, hence no solution. Okay, and just, those of you who like abbreviations, 4 divides 6 is written like that, so 4 doesn't divide 6, hence no solution. So you can just put that as a minimum, but you need the words as well, that conclusion. So that's method 1. Method 2 is just to go straight ahead and use our starred conditions. So this one here. So if I look back at my original equations here, D would be the HCF of 12 and 16. It's 4. It's going to be the same as that. If I work at A minus B, doesn't matter which way around you do it, you might just want to put a modulus sign on there just to emphasise that. And I can see that 4 doesn't divide 6, hence no solutions. So that is all we need to do. Either that or that same amount of marks in an exam. Okay, now sets of 3. Now we are going to go and be solving sets of 3, but just while we're talking about it, I want us to discuss the conditions. So it's a little bit messier with 3. Firstly, each individual congruence must be solvable. If you are given a bunch of congruences like this, that's irrelevant. But quite often you might get, that kind of thing at the start. So you firstly have to solve the congruences, so write them so that they're in the form x is congruent to. So of course you've got to have every individual congruence solvable. If all 3 moduli have no common factors, there'll be a unique solution. So if you've got a modulus of 2, 3 and 5, they are all coprime, so there's going to be a unique solution. However, if you had 2, 3 and 2, 3 and 6, obviously you've got a common factor there. So there still might be a unique solution, but you could have a problem. And that's where the third part comes in. So you could have a problem, but you've got to check within pairs. And of course, the pair you would check is the suspect one. So you'd check the one that had the 2 and the 6 as their modulus. So you'll see why. You'll see how that works in this example here. So this is taken from the textbook. You recognise the typeface. Here I have got 1 mod 2, 2 mod 3, 3 mod 5. Yes, they've got solutions because 2, 3 and 5 and coprime. And it's not just enough to say that the HCF of 2, 3 and 5 is equal to 1. What we're meaning is that 2 and 3 have got HCF of 1, 3 and 5 have got an HCF of 1, and 2 and 5 have got an HCF of 1. So they've all got those individual HCFs being equal to 1. If we look at B, we've got 5 mod 12, we've got 11 mod 13, and we've got 12 mod 14. Now, there is no common factor between all of those 3 numbers. Okay, so we don't have an HCF there, but of course, we do have a highest common factor of something other than 1 between those 2 there. So, we obviously need to look a little bit more closely here. Now you can see they've got 2 different methods. Checking out this bottom one first, we're using the condition. You know that you are looking at these 2 ones, so there's no point in there because they're coprime. That's going to be where the issue is. D is the HCF of 12 and 14, which is 2. You work out the difference between 5 and 12 and you get 7. They've written it as 7 is not a multiple of 2. The way that conditions are written is that 2 does not divide 7, hence no solution. So that's kind of, pretty much an automatic way of doing it. But you'll see here, this is an alternative. And of course, this is something that you can, state if it's applicable. Multiples of 12, all even. 5 above a multiple 12 is always going to be odd. Multiples of 14, always even. If you're adding on 12, you're always going to get something even. That is always going to be odd. That is always going to be even. So there's going to be no solution. Of course, if you have 2 that don't have a solution, there's then no point in checking out the third. Okay. So that's how you check if they have solutions. Let's actually look at now how you would solve the question. So this one here, we have got 3 moduluses there. They've already been written in the solved form, so they've been written as x is congruent to something. If we look at those moduluses there, yep, they, as a 3, highest common factor is equal to 1, but also individually, yep, all of those pairings have got an HCF of 1. So I know I don't have any worries here. I'm going to have a unique solution, and the modulus of that solution is going to be the product of 3, 5 and 7, 105. So solve it. As I've said up here, the method is really just the same as what we do for 2 congruences. We've just got an extra equation, an extra congruence that we need to feed everything through. Right, yesterday when we only had 2, we started with the biggest one. So you might think, okay, well, do I just start with the biggest one? But the way that the equations work, again, we would choose equation 2. You choose the middle one here. That's the way to get the numbers working out nicely for you. So rewrite that, substitute it into the first one. So 4 plus 5a is congruent to 1 mod 3. If I reduce that, that will be a 1. Reduce that, that will be 2 is congruent to 1 mod 3. Subtract the 1s, 2a is congruent to 0 mod 3. And of course, it doesn't matter if you get a 0 there. No, it's fine. It just means it is a multiple of 3. The highest common factor of 2 and 3 is equal to 1, so we can divide that and say, divide that by 2, divide that by 2. So a is equal to a multiple of 3, so let's say 3b. So what I do now is I take that and put it into there. So I get, instead of an expression of x in terms of a, I'm going to get an expression of x in terms of b. So hence x is equal to 4 plus 5 lots of 3b. So 4 plus 15b. So now we have solved 1 and 2. I'm going to take that and I'm going to put it into 3. So I get 4 plus 15b is congruent to 6 mod 7. And here you can see why choosing the middle one to start with was a good idea, because then that mod 5 and that mod 3 combine to give a mod 15. So that is now bigger than that, so it just reduces nicely. If we'd have started with the bigger one and put it in there, we'd have got a 35, which was bigger than we needed to. So reduce that mod 7. Oh, it's nice when that happens. So we have 14, so that's just one above. Subtracts the 4 from the 6. So B is congruent to 2 mod 7. So in other words, B is equal to 2 plus 7C. Substitute back. So I'm going back into this statement here. So I maybe could label what I'm doing a little bit better. I suppose I'm heading it up here, but it's easier to get lost when you've got more equations going on. Substitute back. X is equal to 4 plus 15b, but b I can write as 2 plus 7c. I've fed it through all those equations. That's 30 plus 105c. That's the 105, which is what I expected. And I've got 34 plus 105c. Rewrite as a congruence. X is congruent to 34 mod 105. Okay. There we go. Right, 2 more to do. Won't take long. You'll see there's a very short gap here. So that's not going to be too tricky. You can see straight away here that we may have a potential problem. They've all been written in their solved form. But not all those numbers are co-prime. And we have a highest common factor of 2 there. So what I'm going to do, I'm going to focus on equations 2 and equation 3. I am going to work out the HCF of the moduli. So 6 and 8 is equal to 2. I am then going to subtract those leading numbers there. 7 minus 2 is equal to 5, and then I can say that as 2 does not divide 5, there are no solutions, or there is no solution. Okay, so that's it. That's all you would need to do. You can focus straight on where the problem is. I'm sure some of you have kind of, even more straightforwardly said, well, number one's always even. Always even. Number two, it jumps, doesn't it? Sometimes it's odd, sometimes it's even. So just those two on its own aren't enough, but I know that for sure number 3 is always odd. So alternatively, we could say that equation 1, always even, congruence 3, always odd. So they can never be reconciled, so no solutions. Okay, if you can spot that, but you need the words to back it up. This, some of you might prefer because there are not as many words, but this one in particular, you would need to make sure that you kind of wrote down a full justification why it doesn't work. Okay, so the last one. This one, a little bit more of a drag because we have to firstly solve each one. So 5x plus 1 is congruent to mod 6. Subtract 1 from both sides. 5x is congruent to 1 mod 6. I've got 1 upon multiples of 25. 25 works. So 5x is congruent to 25 mod 6. I can divide that by 5, and you all know why I can divide it by 5. I can divide it by 5 as the HCF of 5 and 6 is equal to 1. Now I'm going to do the middle one. So 3x minus 2 is congruent to 4 mod 7. Add that on, 3x is congruent to 6 mod 7, and that's very nice. I can divide there. And again, this kind of, annoying but necessary step. Marks are given for it, or more crucially taken away in exams if you don't state this. So I'm allowed to do that as the HCF of 3 and 7 is 1. Lastly, the third congruence. If I subtract 1, 2x is congruent to 8 mod 11, I can divide, so go on, then do it. 2x is congruent to 4 mod 11, and in pink, here it comes, as HCF of 2 and 11 is 1. Right, so this is what I'm going to call my 1, 2, and 3. I'm going to start with the middle one, which is number 2. X can be written as 2 plus 7a. I'm going to sub into 1. I'll maybe be a bit careful about my labelling this time, so I'm going to call that star. Put that into 1. 2 plus 7a is congruent to 5 mod 6, and solve that. Reduce that, modulo 6 is going to be 1, so just a single a, and then if I subtract that, I've got 3 mod 6. So a is equal to 3 plus 6b. Put that into star, so I've now, instead of having an expression for x in terms of a, I'm going to have an expression for x in terms of b. X is equal to 2 plus 7 lots of 3 plus 6b. 21, 23 plus 42b. And now I'm going to call that double star. I'm now going to substitute this into number 3. So number 3 is the only one I haven't used yet. So start off with 2, I put it in 1, I've now got to consider it in 3. So x, which is 23 plus 42b is congruent to 4 mod 11. Reduce mod 11, that would be 33, so 9. Subtract that, I think, is negative 19 mod 11. I need this to be a multiple of 9. If I add 22, that gets me 3. If I add on 33, 36. 9b is congruent to 36 mod 11. Just need a bit more room. And as the HCF of 9 and 11 is 1, I can divide both of those by 4. No, I can divide both of them by 9 to get 4 mod 11. So B is equal to 4 plus 11C. And I'm now going to sub that into my double starred expression there. So that tells me X in terms of B, which I've now got B in terms of C. 23 plus 42, 84, 168 plus 462C. 191 plus 462C. X is congruent to 191 mod 462. Okay, so this algebraic method, we really need to know how it works, because you wouldn't want to be writing down all those multiples. I know your calculator, you can write algorithms that very nicely work that out for you, but you need a way of reproducing that in exams. So the algebraic way is the way I want to see, please, in the homework that I will email out later today. First, however, there are a bunch of questions which I don't seem to have to hand. Oh, this might be them. So questions for you to try now. There aren't that many, but certainly for question 2, if you can use the algebraic method, please. Show that something has no solutions, solve those if they can be solved, and then just a little bit of a history problem for the first one. Okay, thank you. Bye-bye. See you next week.